Okay, so welcome to the last class on plane curves today. So we are still in the process of proving the Riemann-Roch theorem, which makes a statement about the space of rational functions that have specified zeros and poles. So it could be recall the setup that we had the last time. Namely, so as usual, f is a smooth projective curve. And on that, we consider a divisor D. And to that, we associated this space that we called capital L of D. And that was defined to be, well, the zero function together with all rational non-zero functions with the following condition on the divisor, namely that the divisor of phi plus D is effective, so greater or equal to 0. So we saw last time that this means intuitively that D specifies maybe some points at which this rational function is allowed to have a pole of at most a certain order, and it might require the function to have a 0 of at least a certain order at some point, and at all the other points there's no restriction. That means it's just a regular function. So that is a vector space we had seen. And its dimension we called little l of D. And the goal is pretty much to compute this little l of D, so to answer how many rational functions there are with certain zeros and poles. And the result that we had last time was just an inequality, but from both sides. So we know already. So if the degree of the divisor is greater or equal to 0, which is pretty much a requirement for that. Otherwise, this is just 0. So then there are no functions like that at all. And then we had the inequality that L of D can be bounded from above by the degree of D plus 1 minus a number G that we call the genus, on this side, sorry, and from the other side, it's deg D plus 1 minus G, where G is called the genus of the curve. And that is the same number that we had seen already in the topological genus when we talked about complex curve in the applications of Bezout chapter. So for us, it's just the definition. It is V minus 1 choose 2. And we saw that it could also be characterized as the smallest number so that this inequality holds. So that means there will be divisors D for which this is actually an equality. There will be divisors for which this is an equality. And so that's sort of the best bound that we can have. So that we saw the last time. And we also saw that this L of D doesn't depend on the degree of D alone. So that means if we fix the degree and then move the points around in the divisor, then this L of D might jump, but it jumps like within these bounds. So we had seen already also that this L of D doesn't depend on the degree of D alone. So that means it's a more complicated question to compute exactly this number. But today, and we'll see in the so-called Riemann-Roch theorem, is that we can make this into an equality by adding a correction term to that. And for that, so the goal for today is we find an equality so that L of D is equal to something, and for that we need the so-called canonical divisor, and that we also introduced. That was the last thing we did last time, for the so-called canonical divisor. That was a divisor that in our definition is really not canonical at all, but looks rather artificial. It is called KF, and it was defined to be D minus 3 times the divisor of an arbitrary line, which we call little l here. So if we pick a different line, there will just be a linearly equivalent divisor. So strictly speaking, this is a canonical divisor class. Then it is well defined at least. The only thing is that it doesn't look canonical because like the factor D minus 3 is sort of artificial. And for that, we had I had already just mentioned last time, that one can show that when one introduces differentials on the curve, differential forms, then one can also assign multiplicities at points to that. So also differential forms can have zeros and poles. So that means there's multiplicities at points. We can add this up formally to get the divisor. So also a differential form has divisors, and the divisor of a differential form is exactly that. So if we compute that, then we'll see that this will be the result. So in brackets, I could just say this is the divisor of a differential form. But we haven't really talked about differential forms here. So this is really just a remark and not something rigorous here in this class. Anyway, for us, this definition here is fine, and we can make do with that. So the first thing we should do is just have a look at what does this divisor look like, and the very first lemma is just a simple computation, namely that the degree of this canonical divisor is in fact related to the genus by the formula. It's always 2g minus 2. And that's actually a very simple computation, because we know kf explicitly and we know the genus explicitly, so that's not too hard. So the degree of kf is, of course, this d minus 3 times the degree of the divisor of L. And this is computable by Bézout, because if we have a line, then this will meet the curve in d points. So the degree of the divisor of a line is d by Bézout. And hence we get the number is d times d minus 3, which is d squared minus 3d. And if we make this into added 2 and subtracted 2, then we can write d squared minus 3d plus 2 as d minus 1, d minus 2, minus 2. And that is up to a factor of 2, just the genus. Right? Genus is d minus 1, d minus 2 over 2. So this is 2g, and here's the minus 2. So that's really just a simple computation, but we'll need this just in a minute. So that's not too, well, I mean, we need to know that, but that's not too hard or interesting. So there's one interesting property, in fact, of this canonical divisor or canonical divisor class, and that's really also non-trivial, and that we want to show now. For that, we need a lot of what we did before, namely the statement is that, as before, so let f be a smooth projective curve, as always here. And we have any point P on F. And the statement is that if we compute the space L of Kf, or just take little l with the dimensions for little l of Kf plus P, then we recall probably that also last time we saw that when you take a divisor and add a point, then this L either goes up by 1 or stays the same. So that was the only possibilities. If we allow for an additional pole at the point P, that will give 1 more or stay the same. And the statement here is, in that case that we start with Kf, it always stays the same. So that means L of Kf plus P is always L of Kf, and it can never be that plus 1. And that will be the key actually to make this into an equality, as we'll see later on. So that is the statement. And as I said, so we know already that in any case we must have this or this plus 1. In that case, we always have that equality. So for the proof, we just start with the simple case first, which is actually easy, namely if the degree is at most 2 of the curve. So if f is less than or equal to 2, then of course by this formula the genus is 0. And that means that d is the degree of the curve, right? I guess I hope I can say that. That will always be like that today. So say of degree d. So if this d, or the degree of f, is at most 2, then the genus is 0 because it has the factor d minus 1 and d minus 2. This means that the degree of the canonical divisor class Kf, which is 2g minus 2, is a minus 2. And hence the degree of Kf plus p is minus 1. It's just one more. And that means both divisors here, Kf and Kf plus p, are both negative degree. And we had seen that whenever a divisor has negative degree, its space L of that will be just a 0 function. Then there is no such rational function that at all. So this means that we also had already seen that then L, capital L of both Kf and also of Kf plus p is both the 0 vector space. And hence this little L of Kf plus p or Kf is both 0. And hence the statement is true, but in the trivial fashion, just with 0 equals 0. So we just want to single out that case because we want this number d minus 3 to be non-negative in the proof so that we can have a certain divisor d minus 3 times, which is a non-negative number of times. So that means from now on we can assume that the degree of f is at least 3. Right again, so d deg f is at least 3. Also, to make computations, we'll just pick a specific line L here for the canonical divisor class. And we want to pick a line that goes through P and is not the tangent. So moreover, so for L in the definition of Kf, choose a line through P that is not the tangent. And that means if we take the divisor of that line, then that contains P, and it contains P only once, and then d minus 1 more other points. Because again, by Bezout, it will meet the curve in d points. Or another way you could say that div L minus P is greater or equal to 0, so it contains the point P. And then the divisor div L minus P doesn't contain P anymore. So that we want to take that particular, well, it's not a particular line, but a line with that property we want to take for L in the definition of the canonical divisor. We've seen already it doesn't matter which one we take. So that means to prove this equality of numbers, we can now just prove an equality of spaces. So we need to show that L of Kf is the, well, Kf plus P is the same as L of Kf, or the capital L, and we know already one inclusion, right? So the space on the right is subset of the space on the left. So with the inclusion this way being clear, well, that means it remains to show the other. Remains to prove that L of Kf plus P is in fact contained in L of Kf. And that's what we actually want to do now, and that for this construction of the canonical divisor with this particular line. So that means we just take an element here in L of Kf plus P and show it's on the right hand side. So to do that, so for that, so let's say phi be an element of L of Kf plus P. So first of all, it is a rational function, so we can write it as f over g for homogeneous polynomials of the same degree. So phi is f over g, with f and g homogeneous of the same degree, And the condition on the divisor is that the divisor of phi plus this thing is greater or equal to 0. So that means the divisor of phi, let's write first like that, plus kf plus p is greater or equal to 0. That's the condition on the space on the left. And plugging in f over g and the canonical divisor means we can write this as div f over g plus d minus 3, well, let's write it this way, say it divisor of L to the d minus 3, and then plus p greater or equal to 0. So that's just the condition that we have here. And I want to bring something on the right-hand side, namely I rewrite it so that the g goes on the right-hand side, and I guess the p as well, and one of the l's. And that means if I take the divisor of f times L to the d minus 2, so I'll leave out one d here, or say take one more, then so that means we add an additive L on both sides. Then on the right hand side, that is first of all we get the divisor of g, and then we have one more L, so the divisor of L, and then we have the minus p. That's just the same equation. I hope I didn't forget anything. So the f and g is in there, the L is there with the exponent of d minus 3 with the 2, and then the p is here, so that should be right. It's the same thing. So why I write it this way is first of all that we had seen, like in our construction for the particular line L, this divisor of L minus p is greater or equal to 0. So that thing here is greater or equal to 0. So we can write this as greater or equal to div g. And whenever we have this situation that the divisor of a particular homogeneous polynomial is greater than or equal to the divisor of another, we have Max-Noether's theorem saying that the remaining divisor comes from another polynomial. And that's what we need here again. So again, the use of Max-Noether's theorem. So saying there will be a polynomial h that makes up for the difference of the two divisors. So that means whose divisor is div f times L to the d minus 2 minus div g. Right. So by Max-Noether. There's a homogeneous polynomial. H, say, and we can in fact also say what the degree is because f and g have the same degree. So that means if there is some other divisor of a function that makes up for this difference, it must have the same degree as that difference, which is L to the d minus 2. So that means this polynomial h must have degree d minus 2. Polynomial h of degree d minus 2, such that the divisor of g, well, h thing is just the difference of the two. So that means the diff of f times L to the d minus 2 minus div g. What that means is just that so div h is div f alpha minus 2 minus div g. So that means if we put that on the other side here again, then what is what we want from that? We can say about div h, put this, take the same inequality as we had there. Div of h is div fl d minus L to the d minus 2 minus div g, which from that here, so put in that thing the first inequality, then this is greater or equal to or div FL v minus 2, I take the first expression there, which is div G plus div L minus P. That inequality of this one here, first one, putting that here, and then we have the minus div G, and that means this is the same here as div L minus P. So that means the divisor of H is pretty much always greater than or equal to the divisor of L, except for the point P. So there would not be true. But at all other points, that means that the multiplicity of the function H is at least the multiplicity of the function L. Okay? So that's by definition of this divisor. It means that if we take the multiplicity at any point Q, which is not the point P, and that of our curve F with H, then this is greater or equal to the multiplicity MQ of our curve F with L at all points except P. So it's not greater or equal to div L, but div L minus P. So if we forget the point P, then any multiplicity here occurs, any point occurs with that multiplicity in this divisor, and it occurs with that multiplicity in this divisor, so it will be greater or equal. So that's an inequality that we have for these multiplicities. Now we have this other statement, which comes from the fact that we call that the local ring of F as a smooth curve is a discrete valuation ring, where we had seen that such an inequality among the multiplicities, which we could always also write as an equality among the ideals, can be written in that form. So that was the statement that we called that OQ. It's a discrete valuation ring. And we've seen quite early that this inequality among multiplicity translates into an inequality of ideals in the other way around. So that means this is the same as saying that the ideal generated by FH is contained in the ideal generated by FL in OQ for all points Q. And I guess the first time it occurred, we call it somehow comparing ideals by intersection multiplicities, and that needed that F is smooth, which is the case here. That was the result that we need here. The reason we're doing that is that we actually want to translate this result among for intersection multiplicities of functions with F to intersection multiplicities of functions with L. So here we have F on both sides in the ideal, and that means that we can rewrite this as divisors of H and L on the curve F, and we want to actually switch the roles of F and L and want to consider functions on the curve L just on the line. And that we can actually do because if this F and H is contained in F and L, note that this also means that the ideal L, H is contained in F, L. It's clear, right? Because if that, I just added L, which is clearly contained on the right-hand side, and I just copied H, which is contained there, right? And I just kept the thing on the right. So that is still true. If this is true, that's quite simple. The point is just that now we have an L on both sides and not an F on both sides. So that means we can interpret this as the coefficient or the multiplicity of H on the line L, and this as the multiplicity of F on the line L. Right? And that's what we want to do now, pass to the line L. Namely, what that means is now we can just go back to the multiplicities. So that means our mu Q of L, H is again greater or equal to mu Q of f comma L. And now we have here the intersection of L and H. And we just sum up all those multiplicities. So summing over all Q, we get the following, namely, we get the sum over all Q. And just take maybe I think we take the sum without P, because there we don't know that this inequality holds. Yeah. So sum over all Q not equal to P of all mu Q of L comma H is greater or equal to, so it's the sum over all Q not equal to P mu Q F comma L. And that is the sum of intersection multiplicities of the line with the curve F, and that by Bezout is, well, if we just take it without P, then by Bezout this will be D. And if we leave out the point P, as L contains this only with multiplicity 1 and is not the tangent, we have at least D minus 1. So that means this is by Bezout, at least D minus 1. So would be, well, in fact, that is actually equal to D minus 1 by Bezout, right? And it's minus 1 because we leave out the point P. But now H has degree D minus 2, and L is still a line. And also by Bezout, this here can have degree at most the degree of H. And at most because we're even leaving out a point. So that means this number is at most D minus 2, but it's at least D minus 1. And so this doesn't work unless we have a common component, right? That's always the thing with Bezout. So Bezout says if we have two curves without common component, then the number of intersection points is that. And so in that case here, as this number here is now less than or equal to, again by Bezout, degree of L times degree of H, which is D minus 2. This is a contradiction unless H has L as a component, which therefore must be the case. And if H has L as a component, that means that the divisor of H on the curve contains the divisor of L. This means that the divisor of H is greater or equal to the divisor of L, clearly. And so let's say where is the divisor occurring? So it's up there. For that thing here, take that expression. Or the divisor of H. A star. So this is greater or equal to the divisor of L. That means f of fl to the d minus 2 minus df g is greater or equal to fl. Bring this on one side, that makes it an L to the d minus 3. And then we're pretty much at our result, because, well, it's still there, but I think we can see it already, because that means that diff of f to the LD minus 3 minus diff g is greater or equal to 0, which we can write as diff f over g plus diff L to the d minus 3, which is the canonical divisor. So here we just have diff of phi plus kf greater or equal to 0. And that means that phi is also not just in LF of k plus p, like there, but also in L of kf. And that shows this inclusion. Let's write this down. So bring all this on one side. This means diff of f LD minus 3 minus div G greater or equal to 0, which means div of, just rewriting stuff, div of f over d plus div of L to the d minus 3 is greater or equal to 0, which means that div phi plus kf is greater or equal to 0, and hence phi is an L of kf. Right? Whereas we started out with phi and L of kf plus p, and now it's also an L of kf, and that shows the other inclusion. So whatever we put up there remains to be shown is exactly this. Hence we have equality, and hence the little l numbers are also the same. But it means there is already quite a subtle argument here that uses things like Bézout and Noether, and it actually, if you check it, uses the exact value of this d minus 3 also. Like for that inequality to work out here, we need actually exactly the number d minus 3 and not anything else. Right? So that the statement of this lemma would be false for different divisors, so you couldn't do it for anything else except for kf. And so that's this. That is this statement. That is pretty much, from the algebraic point of view, the one important property of this canonical divisor kf. That, as I said, for pretty much any divisor d, if you compare L of d to L of d plus p, you don't know what happens. It might stay the same. It might go up by 1. And we had seen when we know that it does go up by 1, but that is the case where we know that it clearly does not go up by 1. And that we can actually use now in the following corollary from that. But maybe first, are there questions on the group as long as it's still here? Right. So then, I had one remark actually first. Yeah, that's a good thing. I think we have enough time for that. Namely, I don't know if that, I think you said there is even in this semester this parallel class on Riemann surfaces, so doing that from a complex analytic point of view, but I think with other topics and not maybe Riemann Roch. But this statement that we just had here, namely that L of kf plus p is equal to L of kf and not bigger, can actually also be interpreted from the complex analytic point of view. And Adam, maybe can I just say in the remark again, because we're not doing complex analysis here. So the complex analysis interpretation. And here I say interpretation, but if we had a complex analysis class on Riemann surfaces, then that we could make this actually into a proof of the same statement. So of the statement L of kf plus p is L of kf, that would be the following. So we had that actually this kf is the divisor of a differential form. And so that means for that we again have to pass these differential forms and say let alpha be a differential form on the complex curve, projective smooth curve. So that means that, as I just said in the remark last time or also today, that there is the notion of divisor of that differential form, and it will be kf by definition. So in a complex analysis class on Riemann surfaces or on complex curves, I would probably define the canonical divisor like that. Now, let's multiply that with a rational function. So we still have a differential form. And think of a rational or a meromorphic function if you're in the complex analysis setting. So phi, we could form phi alpha, which is still a differential form, and multiply them with the function. And we had seen in the last chapter, also in a remark, as it's not our topic here, complex analysis, that there is for these differential forms a residue theorem. saying that if you integrate over differential forms, so the thing that can be integrated over naturally on these manifolds are differential forms. And if we differentiate over that, if we integrate over that thing, then there's the residue theorem, and on a compact complex manifold, this is just saying that the sum of all the residues of that thing is 0. So the residue theorem says that sum over all the residues, all points P and F of this phi alpha. Actually, also just to remember, I mean, that we said actually from the complex analysis class, you would have in mind that if you integrate over a closed path, then the sum of the residues will, I mean, the integral along the path will be the sum of the residues in the interior of the thing. But as we have a compact, complex thing without boundary, we can just take a very small loop and just switch the roles of the interior and the exterior of the loop, right? So that there's no poles in the interior, so that means the result will clearly be 0. But I could also take the exterior of the loop as the interior, and then you get all the residues, and we must get 0. So that is the residue theorem there. And the residue was actually the sum of all the z to the minus 1 parts in the Laurent expansions of these things. But what that means is if the sum is 0, that it's not possible that this thing contains exactly one simple pole and no other pole. Because if it has an exactly simple pole, so of order 1, then it has a residue not equal to 0, because a simple pole means there is a coefficient z to the minus 1 in the Laurent expansion. And at all other points, it's regular. So that's just simply not possible. So that means it's not possible that phi alpha has exactly one simple pole and no other. And no other poles, because at a simple pole the residue would be non-zero, and then the sum cannot be 0 if it's the only point. The residue is non-zero there. And what that means in terms of divisors means if the divisor of phi alpha plus p is greater or equal to 0, which means that we have a differential form that might have a simple pole at the point P, but no other poles, then in fact this also holds without the plus P. So we cannot have the case, so just for a differential form, just allowing one simple pole doesn't help us. Right? That wouldn't work. You don't get any more differential forms. So then the divisor of phi alpha is already greater or equal to 0, right? Because that means you might have a single simple pole at P. Okay, no, it doesn't work, then it's already regular at the point P. And of course the divisor like here, that is the divisor of phi plus divisor of alpha is kf plus P. And that means the divisor of phi plus divisor of kf is greater or equal to 0, and that means the same thing as before. That means that L of kf plus P is L of kf. So that means this lemma that we've just proven and the statement here in the complex analysis world is just the residue theorem. So that is another case where we say, I mean, there's many results. I mean, for complex curves, complex algebraic curves, you can do it algebraically, you can do it analytically, and you will get the same results just with completely different methods. Right? So if we, I mean, here we had Bézout and Max Noether's theorems for all algebraic statements, and here you have the residue theorem for integration along differential forms. So we get the same result at the end. So as to say, that's really nice and just really touching on the relation between algebraic geometry and complex analysis, which can do very similar things. So in that we can use now to make our inequality from the start a little better. Still an inequality, but it's a little better, and we can see that from that we can then get pretty much easily the corollary that we want. Namely, it's another lemma that says the following. So what we need to say, let f be a smooth projective curve as usual. And we need the genus, call this G. And we have D, a divisor on F. And then the statement is, so what we know so far is that if we take L of D, then we have this inequality saying that this is at least equal to deg D plus 1 minus G. That was this one inequality from last time. And I claim that this still holds if we subtract from that L of Kf minus D. So that is a non-negative number, so that's a stronger statement that we still have an inequality like that, even if we subtract this point. And that's another term that is again an L of something, of a related divisor of Kf minus D, which we might or might not know. But then again, we have this smaller, and we have this stronger inequality. And in fact, then I can already, so as a spoiler, so Riemann-Roch will then say that here we actually do have equality, but we'll just see this. That's then very easy. We'll see this after this lemma. So yeah, how do we prove that? That's again an inductive argument. So a claim that holds for all divisors, and we do this by descending induction on the degree. So by descending induction on the degree of D, namely noting that if the degree of D is large enough, namely bigger than the degree of the canonical divisor, then the degree of Kf minus D will be negative, and then this number that we subtract is 0 anyway. And then it's just the old inequality that we know. But that will give us the start of the induction. So the induction start is if the degree of D is greater than 2G minus 2, which was the degree of Kf. Then the degree of Kf minus D is negative. And that means that L of that is 0. And so this is just the old inequality that we know. And that gives us the start of the induction. So that means by induction, we now have to show that if this inequality holds for a divisor D, that it also holds for D minus P. So if we subtract the point, go down with the degree by 1, then it's still true. And then by induction, it holds for all divisors. So the induction step. So let D be a divisor such that this holds. So L of D minus L of Kf minus D is greater or equal to deg D plus 1 minus G. And we'll show the statement for D minus P. Namely that L of D minus P minus L of Kf minus D, and then now we have a plus P here, greater or equal to deg D minus P plus 1 minus G. So if inequality holds for a divisor, it still holds if we subtract a point, And hence we can go down to arbitrarily low degrees and hence to all devices. So to show that, let's just have a look at the term on the left-hand side. So at this L of d minus p minus L of kf minus d plus p, and see what we can say about that. How we can bound this by below, bound this from below. So what do we know? That if we take L of d minus p minus L of kf, and just copy that, kf minus d plus p, then this first term, we saw if d is any divisor, this can be L of d or L of d minus 1. And there was this statement that whenever you add a point, you subtract a point, you either say the same or you change it by 1. So that means as we want, so either as I say it is L of d or it's L of d minus 1. And we want a statement greater than or equal to. So that's the direction that we're interested in. So that means that is, let me first write it down. So this is equal to L of d or L of d minus 1. So that is an exact statement. We know that. And in particular, this means that it's greater or equal L of d minus 1. So we take just the lower of the two numbers to get a bound in that direction. Similar thing here. So L of kf minus d plus p, now just we have a plus p. So this is equal to L of kf plus kf minus d or L of kf minus d plus 1, as we have a plus p. So it's one of the two numbers. Again, we want to have a greater than or equal to, but there's a minus in front. So that means here we do need the inequality in the other direction. So that means it's less than or equal to this number, kf minus d plus 1. And these two inequalities we can put in here to make it a greater or equal altogether. And that means we get an L of d minus 1. And then minus L of kf minus d plus 1. That means we get a minus 1 as the two terms. Then, of course, we plug in this assumption thing here for L of d minus L of kf minus d. So continuing here, right? Continuing here. By a star, we can replace L of d minus L of kf minus d by deg d plus 1 minus g. And then we get a minus 1 minus 1. And that, as we want to have on the right-hand side something with the d minus p, let's rewrite this as the deg d minus p, which actually is deg d minus 1. So that soaks up 1 of the minus 1. So we have plus 1 minus 1. The same number. So that we get in any case. And if you compare it to what we want, it's not quite what we want. We want a plus 1 here. So that means in other words, what we need to show is that we do have a strict inequality here, that it's not greater than or equal to, so that, let me do it in this case here, that in this greater than or equal to, we actually have a greater than, which would mean greater than or equal to with the plus 1. So that needs to be shown. So hence it remains. So so take a different color maybe. In this in that case here we have strict inequality in this greater than or equal to. Because then we would have a greater than deg d minus p minus g, which is the same as greater than or equal to deg d minus p plus 1 minus g. So then we would have namely that L of d minus p plus L of kf minus d plus p is greater or equal to big D minus P plus one more minus G, and that's what we want. So we do that by contradiction. So assume that we do have equality here that we have to rule out. If we had equality, of course, I mean, this inequality comes from two inequalities. So that means if we had equality here on the orange part, we must have equality on both sides. So that means here we must have actually equal to L of D minus 1, and here we must have an equal to L of Kf minus D plus 1. Right? That's the only way we could have equality in this orange circle, namely that both individual terms have equality. So to show this, assume not. Proof by contradiction. So then we have equality in both parts, and here and here. So that means then have L of D minus P is L of D minus 1, and L of Kf minus D plus P is equal to L of Kf minus D plus 1, right? So with equality on both sides. That's the only way we can have equality here. Translated to our space as capital L, this means that this L of D plus P with the capital L is strictly bigger than that. And this, this is strictly bigger than that, and this is strictly bigger than that. So that means the L of D minus P is actually a proper subset of L of D, and L of Kf minus D is a proper subset of L of Kf plus D minus P. Again, so in these, we always have these two choices. If we add a point, the spaces might go up or stay the same. And if we have an equality here with the minus 1 and plus 1, that means that the dimension does go up here, and here also it does go up to that side. And that means that we can pick elements in the complement. So we can pick some phi, which is an L of D, but not an L of D minus P. And we can pick a psi, which is an L of Kf minus D plus P. Kf minus D plus P, but not L of Kf minus D. With on both sides, they are strictly bigger. And that does mean, so if it's an L of D, that means for phi, it means the divisor of phi plus D is greater or equal to 0. And at the point P, this is actually strict. So that means if we compare the multiplicities, I mean, that's no longer true if we put here a D minus P. So that means, let me write this with equality at P. Meaning that the multiplicity of the point P in this expression is actually 0. So we cannot subtract P anymore to get it still greater or equal to 0. And the same here, right? So the divisor of phi plus Kf minus D plus P is greater or equal to 0, again with equality at P. That's what this means. Right? And to multiply these two functions, we take phi times psi, then we would add the divisors. And this means that for phi times psi, by adding these equations, get the divisor of phi times phi plus that is greater or equal to 0, again with equality at P. So you add these two inequalities, and we get divisor of phi times phi plus D plus Kf minus D plus P greater than or equal to 0 with equality at P. And obviously z cancels out. And we have that phi psi lives in L of kf plus p with equality at p. So it means it's not in L of kf. And that's the contradiction to the statement before. So this phi psi is in L of kf plus p. That's exactly this inequality, but it's not in L of kf, because otherwise you wouldn't have equality at p. And that's, of course, contradiction to the lemma before. And that shows this stronger inequality, right? So it's still inequality, but it's stronger because it's the old one, but subtracted something, and it's still true. And that uses the statement from before, like this. And that's why the canonical divisor comes up there, because this canonical divisor has this very special property that adding a point will never change this L space. Right? And that's the only thing that we need, in fact. So in this lemma, that is the only property that we need. So if we had any other divisor on the curve where we knew that passing from the divisor to the divisor plus p would not change this L space, we would get the same statement for that as well. Right? So here we don't use the definition anymore, it's just that property. And the funny thing, I mean, are there questions here? So the funny thing about that is that from that we can get equality actually very easily, namely a corollary from that. And that is now somehow the big theorem here for the end of this whole lecture, whole class, is the so-called Riemann-Roch theorem, which says exactly that, but with an equality. So for any smooth projective f, curve f, and d f of d is g, and the divisor on f, we have that L of g minus L of kf minus d is equal to degree of d plus 1 minus g. And to get it from that inequality, all we have to do is we apply this inequality to kf minus d instead of d. So proof, apply the inequality from last lemma to kf minus d. And so maybe I'll keep the inequality on the board so that we can still see it. And I'll do it here. Minus L of, now it's kf minus d. And on the right-hand side, it's greater or equal to deg of kf minus d plus 1 minus g. So that's what it says. And so that the degree of the canonical divisor is 2g minus 2. So here we have a 2g minus 2 and then minus deg d. It's this degree and then plus 1 minus g. The 2g minus 2 is twice of that. So that means we get this is now equal to g minus, sorted, minus deg d and then minus 1 plus g. And that is precisely the negative of the inequality up there in the same direction, also with a greater or equal to. So if we multiply that with a minus 1, we get the opposite inequality from up there. And so multiplication with -1 gives LD minus LKF minus D is now less than or equal to dec D plus 1 minus D. And together with the lemma up there for D, we get equality. So that's maybe somewhat surprising. So it's like an inequality seems like to be just 1/2 of the statement, but it's a sort of symmetric statement in the sense that when you pass from D to KF minus D, you just exactly get the same in the other direction. Right, so it means that is so for this class, sort of the end, like the big statement. It's, in fact, if you look at any book like on curves, I guess like the Riemann-Roch theorem will always be one of the very prominent theorems at the end. But that means that you can compute how many rational functions with certain zeros and poles there are on a curve. And maybe let's have 2 concrete examples for that at the end. Examples. In the A, this is already a non-trivial statement for D equals 0. For the zero divisor, because of this new correction term, because if you do that, then we know already that L of D is 0, right? I mean, that's just regular functions, and there's only the constant ones. So it's no surprise that L of D is 0, but still Riemann-Roch makes a non-trivial statement also in this case, because it then says L of 0 minus L of, and then KF minus 0, which is L of KF. And on the right side, we have the degree of the zero divisor, which is 0, or plus 1 minus G. And this means, so as this number is, oops, it's 1, sorry, it's constant functions, not 0. So it means we get a 1 here, minus L of KF. And here we get the degree of the zero divisor as 0 is 1 minus G. And hence that L of KF is equal to G. So that means if we interpret, or if we, for example, reinterpret that in terms of our differential forms, this means that the space of all regular differential forms has dimension G. So if we did it like in the complex analysis setting, for example, or he had introduced differential forms, then this would mean that, again, so put this in brackets, that G is the dimension of the space of all regular differential forms. Regular meaning, again, no poles. And that is yet another way to define the genus. And if you, again, look into books, so the genus occurs all over the place. So if you do anything a little more serious with curves than just like drawing pictures or so, then you will run into the genus at some time. And there's so many ways to define that, and that would be another way. So if you introduce differential forms just that are regular, that are not have not poles anywhere, and ask how many of them there are, then you would get exactly back the genus, right? The dimension of space of that space is another way to define. Another example B is in many cases where one applies Riemann-Roch, actually one wants one of those two terms to be 0, so that you get out of this problem that you, in general, probably you know neither this nor that number. But if the divisor is big enough from the degree, we can take the same case that we had here in the beginning of the proof, namely if the degree of D is big enough so that the degree of KF minus D is 0, we know that this is 0, and then we have this new statement now with an equality. So B, if the degree of D is greater than 2G minus 2, then in the same way as in the start of the proof of this first inequality, then the degree of kf minus d will be less than degree of k minus degree of g, so less than 0. And hence we get that L of kf minus d is 0. And hence Riemann-Roch will tell you an equality statement that contains only one of these two numbers. And then we get L of d is actually equal to d plus 1 minus g. And if you check this for all the example cases that we had, where we saw that this is actually in general an inequality, so that means that we don't have equality in general, so it might be smaller here. These were all cases where the degree of the divisor was not too big in that sense. Right? Whenever you have very big degrees, then this will be actually an equality, and that results sort of always. So that means there will be yet another way to define the genus, right? If you take for large enough d, so after some bound, eventually for some degree d big enough, you get this genus. Yeah, so that's just two simple applications. And if you just do like the theory of curves, maybe not just for plane curves, then of course to go on some more. I mean, the first thing if we went on from that would be at some point one would have to get out of this restriction that we have plane curves. And that's a very serious restriction actually. So which basically disallowed us to talk about morphisms or anything, right? Because there's always this embedding of curves in something which is not very natural. So if you did algebraic geometry, for example, later on, then of course all these curves will be examples, the big example class. And then they do not lie inside some ambient space necessarily, and then you can take about morphism, for example. But still, these results, of course, are all true. And many curves can actually be represented as plane curves, and many will occur as plane curves. So that's why it's still like very, important results and that we got here. I think it should give a nice introduction, or at least a nice idea what algebraic geometry in general is. I mean, what we did now is essentially throughout the whole class is, so first of all, we used algebraic methods, meaning like studying polynomials, rational functions algebraically to derive all possible results maybe on whatever type, be like topological type, or here like how many functions we have, how many intersection points we have just from algebra. But we saw that in pretty much any case you could do it also using different methods if you wanted to, being like topological methods, analytical methods, number theoretic methods. We saw like when we discussed elliptic curves. So there's lots of relation to other fields. Right. Yeah, so that's the class then. I think, any questions? Yeah? Then I hope that you enjoyed it sort of, and it gave you a nice introduction to algebraic geometry. And that might be something where you may want to attend the actual algebraic geometry class then sometime later on. Okay, so then that's it.